Well, you've just seen simple perturbational analysis of some programs. I took a program that was very similar to another program and looked at them both and saw how they evolve processes. I wanted to give you some variety by showing you some other processes and shapes they may have. Again, we're going to take very simple things, programs that you wouldn't want to ever write. They would be probably the worst way of computing some of the things we're going to compute. But I'm just going to show you these things for the purpose of feeling out how a program represents itself as the rules for the evolution of a process. So let's consider a fun thing, the Fibonacci numbers. You probably know about the Fibonacci numbers. Somebody, I can't remember who, was interested in the growth of piles of rabbits, and for some reason or other, the piles of rabbits tend to grow exponentially, as we know. And we have a nice model for this process is that we start with two numbers, 0 and 1, and then every number after this is the sum of the two previous. So we have here a 1, then the sum of these two is 2, the sum of those two is 3, the sum of those two is 5, the sum of those two is 8, the sum of those two is 13, this is 21, 34, 55, etc. If we start numbering these numbers, say this is the 0th one, and the first one, and the second one, and the third one, and the fourth one, etc. This is the 10th one, 10th Fibonacci number. These numbers grow very fast, just like rabbits. Why rabbits grow this way, I'm not going to hazard a guess. Now I'm going to try to write for you the very simplest program that computes Fibonacci numbers. It's what I want is a program that, given an n, will produce for me Fibonacci of n. Okay? I'll write it right here. I want the Fibonacci of n, which means this is the n, and this is Fibonacci of n. And here's the story. If n is less than 2, then the result is n, because that's what these are. That's how you start it up. Otherwise, the result is the sum of fib of n minus 1 and the Fibonacci number, the n minus 2. So this is a very simple, direct specification of the description of Fibonacci numbers that I gave you when I introduced those numbers. It represents the recurrence relation in the simplest possible way. Now, how do we use such a thing? Let's draw this process. Let's figure out what this does. Let's consider something very simple, like computing Fibonacci of 4. To compute Fibonacci of 4, what do I do? Well, it says it's not less than 2. Therefore, it's the sum of two things. Well, in order to compute that, I have to compute then Fibonacci of 3 and Fibonacci of 2. In order to compute Fibonacci of 3, I have to compute Fibonacci of 2 and Fibonacci of 1. In order to compute Fibonacci of 2, I have to compute Fibonacci of 1 and Fibonacci of 0. In order to compute Fibonacci of 1, well, the answer is 1. That's from the base case of this recursion. And in order to compute Fibonacci of 0, well, that answer is 0 from the same base case. And here's a 1. And Fibonacci of 2 is really the sum of Fibonacci of 1 and fib of 0. And in order to compute that, I get a 1. And here I've got a 0. I've built a tree. Now, we can observe some things about this tree. We can see why this is an extremely bad way to compute Fibonacci numbers. Because in order to compute Fibonacci of 4, I have to compute Fibonacci of 2 subtree twice. Okay? In fact, in order to add one more, supposing I want to do Fibonacci of 5, what I really have to do then is compute Fibonacci of 4 plus Fibonacci of 3. But Fibonacci of 3 subtree has already been built. Okay? This is a prescription for a process that's exponential in time. To add 1, I have to multiply by something because I take a proportion of the existing thing and add it to itself to add one more step. So this is a thing whose time complexity is order of, actually it turns out to be Fibonacci of n. Okay. This is a thing that grows exactly as Fibonacci numbers. It's a horrible thing. You wouldn't want to do it. The reason why the time has to grow that way is because we're presuming in the model, the substitution model that I gave you, which I'm not doing formally here. I sort of now spit it out in a simple way, but presuming that everything is done sequentially, that every one of these nodes in this tree has to be examined. And so since the number of nodes in this tree grows exponentially, because I add a proportion of the existing nodes to the nodes I already have to add 1, then I know I've got an exponential explosion here. Now, let's see if we can think of how much space this takes up. Well, it's not so bad. It depends upon how much we have to remember in order to continue this thing running. Well, that's not so hard. It says, gee, in order to know where I am in this tree, I have to have a path back to the root. In other words, in order to, let's consider the path I would have to execute this. I say, oh yes, I'm going to go down here. I don't care which direction I go. I have to exit it, do this. I have to then do this. I have to traverse this tree in this sort of funny way. Okay. I'm going to walk this nice little path. I come back to here. Well, I got to remember where I'm going to be next. Got to keep that in mind. So I have to know what I've done. I have to know what's left. In order to compute Fibonacci of 4, at some point I'm going to have to be down here. And I have to remember that I have to go back to here, and then go back to here to do an addition, and then go back to here to do an addition of something I haven't touched yet. The amount of space that takes up is the path, the longest path. You know, how long it is. And that grows as n. So the space, because that's the length of the deepest line through the tree, the space is order of n. It's a pretty bad process. Now, one thing I want you to see from this is a feeling of what's going on here. How is this program related to this process? Well, what are we seeing here? There really are only two sorts of things this program does. This program consists of two rules, if you will. One rule that says Fibonacci of n is this sum, which you see over here, which is a node that shapes like this. It says that I break up something into two parts. Under some condition over here, if n is greater than 2, okay, then the node breaks up into two parts. Less than 2. No, it's greater than 2. Yes. The other possibility is that I have a reduction that looks like this. Okay? And that's this case. If it's less than 2, the answer is n itself. So what we're seeing here is that the process that got built locally at every place is an instance of this rule. Here's one instance of the rule. Here's another instance of the rule. And the reason why people think of programming as being hard, of course, is because you're writing down a general rule, which is going to be used for lots of instances, that a particular instance is each particular instance control each particular instance for you. You've got to write down something that's sort of general and in terms of variables, and you have to think of all the things that could possibly fit in those variables, and all of those have to lead to the process you want to work. Locally, you have to break up your process into things that can be represented in terms of these very specific local rules. Well, let's see. Fibonacci's are, of course, not much fun. Yes, they are. You get something called the golden ratio, and we may even see a lot of that sometime. But let's talk about another thing. There's a famous game called the Towers of Hanoi, because I want to teach you how to think about things recursively. The problem is this one. Okay? I have a bunch of disks. I have a bunch of spikes. And it's rumored that somewhere in the Orient there is a 64 high tower, and the job of various monks is to move these spikes in some complicated pattern. So eventually I move all of the disks from one spike to the other. And if it's 64 high, and it's going to take 2 to the 64th moves, then for a long time. The claim is that the universe ends when this is done. Well, let's see. The way in which you would construct a recursive process is by wishful thinking. You have to believe. Okay? So, the idea, supposing I want to move this pile from here to here, from spike 1 to spike 2. Okay? Well, that's not so hard. See, supposing somehow, by some magic, because I've got a simpler problem, I move a 3-high pile to here. I can only move one disk at a time, so I'm not telling you how I did it. But supposing I could do that, okay? Well, then I could just pick up this disk and move it here. And now I have a simple problem. I have to move a 3-high tower to here, which is no problem. So by 2 moves of a 3-high tower plus 1 move of a single object, I can move the tower from here to here. Now, whether or not it's not obvious in any deep way that this works. And why? Now, why is it the case that I can presume, maybe, that I can move the 3-high tower? Well, the answer is because I'm always counting down. And eventually I get down to a 0-high tower, and a 0-high tower requires no moves. So let's write the algorithm for that. It's very easy. I'm going to label these towers with numbers, but it doesn't matter what they're labeled with. And the problem is to move an n-high tower from a spike called from to a spike called to with a particular spike called spare. That's what we're going to do. Using the algorithm I informally described to you, move of an n-high tower from to with a spare. Well, I've got 2 cases, and this is a case analysis, just like it is in all the other things we've done. If n is 0, then I'm going to put out some answers. Done, we'll say. I don't know what that means, okay? Because we'll never use that answer for anything. We're going to do these moves. Else, I'm going to do a move. Move a tower of height less than n, the decrement of n, height. Now, I'm going to move it to the spare tower. The whole idea now is to move this from here to here, to the spare tower. So from to spare, using 2 as the spare tower. Okay? Later, somewhere later, I'm going to move that same n-high tower, after I've done this, going to move that same n-1 high tower from the spare tower to the to tower using the from tower as my spare. So, the spare tower to the to tower using the from as the spare. All I have to do now is, when I've gotten it into this condition between these 2 moves of the whole tower, if I've got it into that condition, now I just have to move one disk. Okay? So I'm going to say there's something for printing a move, and I don't care how it works. from the 2. Now you see the reason why I'm bringing this up at this moment is this is almost identical program to this one in some sense. Okay? It's not computing the same mathematical quantity. It's not exactly the same tree, but it's going to produce a tree. The general way of making these moves is going to lead to an exponential tree. Well, let's do this 4 high. Okay? Now I have my little crib sheet here. Okay, so otherwise I get confused. Well, what I'm going to put in is the question of move a tower of height 4 from 1 to spike 2 using spike 3 as a spare. That's all I'm really going to do. Okay, well, let's just do it. I'm not going to worry about writing out the trace of this. You can do that yourself. Okay? But it's very simple. I'm going to move disk 1 to disk 3. And how did I get to move disk 1 to disk 3? How do I know that? Well, I suppose I have to look at the trace a little bit. Okay? What am I doing here? Well, this is not, n is not 0. So I'm going to look down here. This is going to require doing 2 moves. I'm only going to look at the first one. It's going to require moving. Oh, why do I have move tower? It makes it harder for me. Move. Okay? I'm going to move a 3 high tower from the from place, which is 4, to the spare, which is 2, using 3 as my, no, using from, yes, I'm sorry. Okay, from 1 to 3 using 2 as my spare. That's right. Okay, and then there's another move over here afterwards. Okay, but now I say, oh yes, that requires me moving a 2 high tower from 1 to 2 using 3 as a spare and some other things. And that's going to require me moving a 1 high tower from 1 to 3 using 2 as a spare. Right? Well, and then there's lots of other things to be done. So I moved my 1 high tower, okay, from 1 to 3, using 2 as a spare, which I didn't do anything with. Well, this thing just proceeds very simply. I move a disk from 1 to 2, then I move this disk from 3 to 2. Okay, and I don't really want to do it. Then I move from 1 to 3. Then I move 2 to 1. Right? Then I move 2 to 3. Then 1 to 3. 1 to 2. Okay. 3 to 2. 3 to 1. It's all got worked out beforehand, of course. 2 to 1. 3 to 2. 1 to 3. Okay. Oh, 1 to 3, excuse me. Thank you. 1 to 2. Okay. And then 3 to 2. Whew. Now, what I'd like you to think about, okay, you just saw a recursive algorithm for doing this, and it takes exponential time, of course. Now, I don't know if there's any algorithm that doesn't take exponential time. It has to. If I'm doing one operation, and I can only move one thing at a time, there's no algorithm that's not going to take exponential time. But, can you write an iterative algorithm rather than a recursive algorithm for doing this? One of the little sort of things I'd like you to think about. Okay. Can you write one that, in fact, doesn't break this problem into 2 subproblems the way I described, but rather proceeds a step at a time using a more local rule? That might be fun. Thank you so much for the 3rd segment. Are there questions?
What's a typical way to reduce the tree recursion problem? How do you save, for instance, the intermediate work you have done in computing the Fibonacci?
Oh, well, that's in fact one way. That's one of the ways to do it is what you just said. You said, I save the intermediate work. Okay, well, let me tell you, this again we'll see later, but suppose it's the case that anytime I compute anything, any one of these Fibonacci numbers, I remember it in a table. It takes only linear time to look up the answer. Then if I ever see it again, instead of doing the expansion of the tree, I look it up. I've just transformed my problem into a problem that's much simpler. Now, of course, there are other ways to do this as well. That one's called memoization, and you'll see it sometime later in this term. But I suppose there are just very simple linear time and, in fact, iterative models for computing Fibonacci's. And that's another thing you should sit down and work out. And that's important. It's important to see how to do this. I want you to practice.